So last time we talked about how the kinetic energy is 1/2 m times the square of the velocity. If you write that in terms of your generalized coordinates and your generalized momentum and time, you get your kinetic energy, traditionally called T, expressed correctly. If you also write the potential energy, same thing as last time, traditionally called V, in terms of your generalized coordinates Q, your momentum, and your time, and the momentum depends on your Q. But then you can get the whole energy, potential plus kinetic energy, written in terms of Q, P, and T. And I'm making a big deal of what it's in terms of as a function because we're going to want to take its partial derivative. So the partial derivative of this expression, we need to know that V depends on Q. So its partial with respect to P's are 0. And this is partial with respect to Q is 0. So let's take H, take its partial with respect to Pj, and the potential doesn't depend on Pj, it just depends on Q. So it's going to give us 0. And if we take the partial of this, that's a dot product of two vectors. So write it out as the sum of the square of the components. And we're taking the partial with respect to Pj. So for all the i's that aren't equal to j, they're going to go to 0. And we're just going to get 2 comes down, get a 2pj divided by 2m, and we just get pj over m. And if you think of p as your generalized coordinate times your mass, that's just q dot. So that's fine. Q dot component, the j, gives us that. If instead you take the partial of h with respect to qj instead of pj, then this time, this is not going to be 0, but this one is. This one's in terms just of p, and this is a partial. We're very clear that the function is a function of q and p and t, so this baby is going to be 0. The gradient of this potential, that's how we define the potential, so it's gradient plus force. The negative of the gradient of this is going to be the force, so the jth component of the gradient is this, so that's the jth component of the force, so that's mass times the jth component of the acceleration. So we get negative total time derivative of m times 1 derivative of the generalized coordinate. That's just momentum, so we get negative of p dot. There's an asymmetry here. We take the derivative of h with respect to p, we get q dot. We take the derivative of h with respect to q, we get negative p dot. And remember, each of the j's goes next. So we're going to write this as a matrix. One way to think of a function of two vectors is as a function of a really long vector. So what if h took as its input, list all the components of q, then list all the components of p, then list time. So h is taking this really long vector as its input. That's one way to think of this original function. So now let's look at these partials. If I take the total time derivative of this vector that's twice as long, x, y, z, momentum, x component of momentum, y component of momentum, z component of momentum, then we'd expect a 6 vector output. Q dot over here was just partial h with respect to j. So think of this kind of a gradient kind of operator. And if we take the negative of the gradient with respect to q, we're going to get the p dots. This is sort of silly notation. I just want to make it really clear that if you just had a matrix like this, you can take an actual gradient of h as a function of the long p and q vector. You'd get a 6 vector. The first 3 components would be with respect to q. So over here we'd get a minus sign, and then they'd appear in the lower part. And then the next 3 vectors would be, 3 components would be the p vectors. And then multiply out here, so the bottom part of the vector, the right side here, and so we get exactly what we wanted for the changes in Q. I'm going to check to see if that shows up on the screen. And it doesn't. The actual gradient of f of h is going to have 3 components here, 3 components here, so it's going to be a component with 6 vectors. The 3 that are the partial with respect to q are going to hit here and give 0, and here they're going to give negatives. Negative partials with respect to q of h, great. The next 3 are going to be the partials with respect to the next parts of the input, so that's p. They hit here, give you the partial with respect to p. So you get all the components there. So it's traditional to call this matrix J. It has a nice property that you square it, and you're going to get -1. These are just block diagonal matrices. Here's a 3 by 3 identity matrix, 3 by 3 identity, the 0 matrices. So we can call that J. In R3, there's a norm you're used to. You can take any 3 vector, you can take its, write it as a column vector, you can take its transpose and then multiply by itself with the regular matrix product. You'd get the inner product. You can even have different vectors. So if you had a V and a W, they're both in R3, you could imagine taking the transpose of V and then just do matrix multiplication to get a scalar. With the J, we can define a new bilinear form. This bilinear form, you'd want to take vectors that are not just ordinary 3 vectors, but are these compositions. The first 3 components are Q, the 4th, 5th, and 6th components are P. And what you do, we call this form omega. You just take the transpose of your original vector. You take the matrix J over here, 6 by 6 matrix. You multiply by this 6 space column vector. So column vector, square matrix, you get a column vector, row vector, you just get a scalar. In that sense, it's just like an ordinary inner product. And in fact, the book mentions all the properties it has, which is that it is linear, and that if you were to fix everything and just take 2 vectors here and add them together or scale them, then to get the sum of their answers, or the scalar. It's anti-symmetric, and so one of the differences between it still has one nice property with the regular inner product, which is if this inner product is 0 for all W, then the V itself is 0. I'm going to do a one-dimensional example to help you see this. By one dimension, I mean our Q only has one dimension. So you can imagine here's a good old row vector. Here's our Q, here's our P, here's our J matrix. Our J matrix has an identity matrix. We're just doing 1 by 1. So this is a block matrix. And then we multiply it by delta stinking quarter alpha, beta, gamma, delta. But when we do the matrix multiplication, we're going to get alpha, beta. We're going to switch them so the delta is on top. Delta, gamma, and the gamma has a minus. Regular matrix multiplication here, so we get alpha, delta, minus beta, gamma. And clearly, if this were 0 for all deltas and gammas, then specifically it would be 0 if this one was 0, and that one was 1, so therefore we conclude that beta would have to be 0. And if this is 0 for every gamma and delta, then it would have to be the case that when this one was 0 and this one was 1, we also get 0. So A would have to be 0. So both of these would be 0, so B would be 0. That's what the non-degeneracy goes. Now, beef this up. We've got a P1. This is as a row vector. Sorry. Q1, P1, P2, P2. So I apologize that these are row vectors over here. Q, P. Over here you've got P minus Q. But now it's column vector, row vector, so it's just normal dot product you're used to. Q1 dot P2 minus Q2 dot P1. So in a sense, this bilinear form isn't mysterious. If you know your P's and Q's, you're just taking a P and a Q from two different spaces, taking their inner product, for the two different vectors, and you're putting them in an anti-symmetric fashion. So if someone gave you the same vector here and the same vector here, with the ordinary inner product, you'd get the squared length, you'd get something not 0 unless the thing was 0. In this case, if you stick the same thing in, regardless of what it is, you always get 0. Because the Q1 would be the same as Q2, the P1 would be the same as P2. That's what they mean by anti-symmetry. And I apologize if I started talking too quietly there.